If you're like me, when you think about analytics or big data, the first thing that comes to mind is a massive pile of files sitting somewhere in a data lake, probably an S3. For years, data lakes were really simple. They were Parquet files organized into directories, and those directories corresponded to partitions. If you don't know Parquet, it's a columnar storage format that is really efficient to scan. And why scan? Well, that is the most common operation in OLAP or analytics type queries. You've got a bunch of records and you have to read all those records as quickly as possible and usually compute some aggregate over some value in those records. So it's efficient to scan, and scanning is very important in analytics. So anyway, you dump these Parquet files into S3 at hard-coded paths. Then you would write, in the bad old days, MapReduce programs in Java to process them. These were not really fun times. You filtered partitions by hand and just hoped nobody else was writing to the same location at the same time as you were reading. There were no transactions. Schema changes broke pipelines all the time, and figuring out what data was current was a nightmare. It kind of worked, but it was fragile, error-prone, and you could never really guarantee correctness. In 2008, Hive changed the game. It brought table formats to data lakes, adding schemas, partitions, and the best thing, a SQL interface. Suddenly, you could just write select star from sales instead of some weird 200-line Java program jammed into a function called map and a function called reduce in ways that were really not pleasant to think about. But it didn't take long for new problems to surface. Schema evolution was limited. You want to add a column? Well, okay. But rename or drop a column? You had to rewrite the whole table, actually copy it from one place over to another. Partitions were hard-coded into the directory structure. If you pick wrong at the time you create the table, you're stuck. Slow queries or a full rewrite. And no transactions for years, so concurrent writes would corrupt data. ACID finally arrived in 2014, but only with ORC files in that format. And it created Delta files needing constant compaction to keep queries fast. And this was all built for Hive. Other engines could connect to the data lake, but it was never really seamless. In 2017, engineers at Netflix looked at this mess and decided to start over, design it right from the ground up. They built Iceberg, an open table format that treats data lake files like actual database tables, with all the guarantees that you've come to expect from a transactional database. Like Hive, you get SQL tables with schemas and partitions. But unlike Hive, you also get real ACID transactions, schema evolution that actually works, time travel, hidden partitioning that adapts as your queries change, and the ability to change the partitioning scheme over time. And here's another difference. Hive stored its metadata outside the data lake. Iceberg stores metadata right alongside the data. Everything lives in the lake. Let's look at how Iceberg actually organizes a table. An Iceberg table starts with a data layer at the bottom there, the actual files that hold your data. And we call those, famously, the data files. The files are immutable. Once they're written, they can't be changed. If you want to update a row, Iceberg writes a new file, and we'll talk about how later. But that's a typical thing in data lakes and in analytics systems. We normally think of analytics as backward looking at events, at things that have happened in the past, which are, as we know, immutable. That's not always the case, and we'll talk about upserts later on. The format of those data files is usually Parquet. That's probably what you're going to find in the wild, but it doesn't have to be. They can be ORC, they can be Avro, whatever you like. But again, typically Parquet. Next up is the metadata layer. There's a lot of complexity in here. This is where Iceberg really starts to get interesting. The metadata layer tracks everything about your table: schema, partitions, which files contain which data, even statistics like min, max values per column, and things like that that will help with scanning later on. This is all the data about the data. Iceberg's metadata is organized into kind of a tree here, and the names can be a little tricky the first time through. Sometimes you can get them mixed up, so follow closely. At the bottom, these are the manifest files. Each manifest tracks a set of data files along with stats. Again, things like row count, min, max values for numeric columns, partitioning information, things like that. This is what lets query engines skip entire files without even opening them. If you want sales from January and you know that these 47 files have nothing from January, you can skip them. And you could tell that possibly just by looking at the metadata. Like data files, manifests are immutable. They never change once they're written. One level up, we have manifest lists. These are lists of manifest files. Each one points to a bunch of manifests and tracks their combined stats. How many files in that list of manifests, which partitions are covered, what ranges, those stats are kind of rolled up into the manifest list. And this adds another level of pruning. If you have a query filtering on January 2025, Iceberg can skip an entire manifest list if it knows it only covers dates in 2024 and never needs to open a single data file. And again, manifest lists, immutable. At the top is the metadata file. This is the single source of truth for a table. It's got the schema, it's got the partitioning strategy, table properties, and most importantly, a thing called the snapshot history. Snapshot, you say? Well, yes, a snapshot is a version of the table at a specific point in time. You think of it like a Git commit. If you know how Git works, that's going to help you a lot with thinking about time travel, branching, tagging, snapshotting, all of these things in Iceberg. The snapshot captures the state of the table, and once it's created, it's frozen. That's it. That snapshot is frozen for all time. Here we have snapshot S0 pointing to our manifest list. Each snapshot has an ID and a timestamp and points to a manifest list. And I sure hope you see this coming. Metadata files are immutable too. Everything in Iceberg is write once and never change. So if everything's immutable, how do you add data? Well, simple. You write new files at every level. New data comes in, Iceberg writes new data files. Then, what's it going to do? It's got to create a new manifest pointing to those files. And that new manifest, a new manifest list gets created too, referencing the old manifests and the new one. So this is data being added to a table. So we'll just point to all those manifest files and add our new manifest file to this manifest list. And of course, we're going to need a new metadata file with a fresh snapshot. That snapshot is going to point to the new manifest list. All those old files are still there, unchanged. And that's going to support time travel later on. And if you look closely here, you'll see that that old snapshot is available too. So that state of the database, we still know about that, even though we've mutated it and added data to the table in the current snapshot. So how does a query engine know where this metadata file is located? You think about that. That's some path in an S3 bucket. That's a horrible name. It's some big long thing. You don't want to be copying and pasting that and managing that everywhere. You want a nice table with a name like sales or meetups or something like that. That's where the catalog comes in. And we're going to cover this catalog in depth next. So that is the basic Iceberg architecture. Data files at the bottom, manifests track the data files, manifest lists organize the manifests, and then metadata files tie it all together. The catalog, kind of on the outside, points to the current metadata file with a nice friendly name that a human can deal with. Everything in there is immutable. That's what makes time travel, transactions, and schema evolution all possible. Next up, like I said, the magic of the catalog.